Armando Hasadungan, biology and medicine videos. Please make sure to subscribe, join the forum and group for the latest videos. Please visit Facebook Armando Hasadungan. Please like, and here you can also ask questions, answer questions, and post some interesting things, including your artworks. And you can also change the quality settings to the highest one for better graphics. In this video, we're going to continue on from where we last left off, urine production. And remember that there are three major renal processes: filtration, reabsorption, secretion, and the fourth one we can say is excretion. Let's begin looking at urine production by firstly looking at filtration, glomerular filtration, which is the first step in urine production. So, plasma volume entering the afferent arteriole is about 100%. 20% of this is filtered into the nephron, leaving 80% still in the arteriole, in the bloodstream. This 20%, which have just been filtered, more than 19% of it will actually be reabsorbed by the blood. And so more than 99% of the plasma return to systemic circulation from entering the afferent arteriole, meaning that we have less than 1% of the volume of the plasma actually excreted. I hope this makes sense. An important terminology to know is filtration fraction. Filtration fraction is the amount of plasma filtered from the glomerular into the nephron, and this is 20%. Now let's look at how the substances actually get filtered from the glomerular into the nephron. So here I'm drawing the afferent arteriole and the efferent arteriole. The efferent arteriole coming in and the efferent arteriole going out of the Bowman's capsule. Here are the glomerular capillaries, and this is the Bowman's capsule. We have special cells surrounding this area known as mesenchymal cells. Mesenchymal cells contain actin, which perform contraction and so have an important role in altering blood flow. And then we have these other cells surrounding the arterioles known as granular cells. And if you remember, they're the cells that secrete the hormone renin. And then we have the thick ascending limb, which passes in close contact to the head of the nephron. And this is because they contain special cells known as macular dense cells, which are chemoreceptors, which help balance ion levels of sodium and chloride passing through. And finally, the most important thing we should know is that there are podocytes in the glomerulus. Podocytes are important in the filtration process, which is the first step in urine production. Podocytes have many feet-like projections. Let's have a look at how substances get filtered and how podocytes are important in this process by taking a cross-section of this glomerular capillary. So here we have the actual capillary. And here we have mesenchymal cells. Podocytes surround the capillaries with its many feet-like projections, like so. Remember, inside the capillary we have ions, we have red blood cells, solutes essentially. Let's take a closer look at this membrane, these membranes, and how substances get filtered. Just a quick look. The first membrane is the capillary's endothelial cells, which are fenestrated, which means that they have gaps, allowing for solutes to move from the capillary into the nephron. The second layer we have the basement membrane, where solutes can still easily pass through. The outer layer we have podocytes, feet-like projections of podocytes, the foot of the podocytes, and they are spaced out, or they can be very close together, and they will have also gaps between them, allowing for filtration. The endothelial cell, the basement membrane, and the podocyte make up the group of membranes known as the filtration membrane. Now, the filtration membrane being that where there is a gap is they make a filtration slit, which means that substances can actually get filtered from the capillary into the nephron. The filtration membrane controls what type of substances moves into the nephron. They actually do not allow big molecules to move through, and they do not also allow big negatively charged molecules to pass through. Why is this? Well, let's have a look again at here we have the glomerular capillary, and we have substances within this glomerular capillary. We have negatively charged proteins, we have negatively charged ions such as chloride, we have positively charged ions such as sodium, and also we have a negatively charged protein such as albumin. Now, the podocytes and the basement membrane are actually overall negatively charged due to proteins and carbohydrates on them known as proteoglycans. So because of proteoglycans, podocytes and basement membranes are overall negatively charged. What does this mean? It means that positively charged molecules are absorbed more readily and easily than negatively charged molecules. For example, albumin, which can actually pass through because of its good size, doesn't pass through because it is negatively charged, and so negative repels negative. Sodium can easily pass through because it is positively charged, and so it's attracted. Chloride can actually pass through because it is very small, and even though it's negatively charged, it can still pass through. However, these big negatively charged proteins, they will never pass through because, for one, they are too big to pass through, and second, they are negatively charged, and so repel the negativity of the podocytes and the basement membrane, basically the glomerular capillary. Okay, so we know that substances can move from the glomerular capillary into the nephron because of these filtration slits. But what causes them to move from the glomerulus into the nephron? Well, pressure causes them to move from the glomerulus into the nephron. So let's look at filtration pressure and how it causes these substances to move from the glomerulus into the nephron. Sorry, I'm saying glomerulus and nephron like 20 times. So here we have the head of the nephron, the Bowman's capsule, and the glomerulus capillary. Afferent arteriole going in and afferent arteriole going out. Let's first of all look at the pressures that favor filtration, which is outward movement, out of the glomerulus. And this pressure which favors filtration is known as the glomerular hydrostatic pressure, abbreviated P for pressure, GH. And this is about 60 millimeters mercury. And then we have pressures that opposes filtration, and this is inward, so substances moving back into the glomerulus. And these pressures are the Bowman's capsule pressure, abbreviated P for pressure, BC, and this is about 16 millimeters mercury. And then we have another one which opposes filtration, which is glomerular colloid osmotic pressure, P for pressure, GCO, and this is about 34 millimeters mercury. So what does this all mean? Well, the net filtration pressure, NFP, would be the outward pressure, or meaning the movement out of the glomerulus, minus the inward pressure, the movement into the glomerulus. So to calculate the net filtration pressure, it would be pressure of glomerular hydrostatic pressure minus the Bowman's capsule pressure minus the glomerular colloid osmotic pressure. So it's 60 minus 16 minus 34. And this gives us 10 millimeters mercury, positive 10 millimeters mercury in the filtration direction. So it means that the net filtration would be 10 millimeters mercury. And also remember that this pressure and direction makes it favor filtration. Next concept to understand is what's called GFR, the glomerular filtration rate. GFR is the volume of fluid that filters into the Bowman's capsule per unit of time. And this is, on average, for a human, 125 mils per minute or 180 liters a day. So this is just the amount filtered. But remember that less than 1% of the volume is actually excreted. So to find GFR, we have to find Kf and times it by the net filtration rate. We know what the net filtration rate is. It's about 10 millimeters mercury, right? The Kf is a glomerular capillary filtration coefficient, and this is calculated or found by measuring the surface area of the glomerular capillary available for filtration and also its permeability. I'm not going to really talk about the Kf, but this is just important to know how to calculate the glomerular filtration rate. So why is it important to know how to calculate GFR? Well, if we know that Kf times net filtration rate equals GFR, we know that if we alter the net filtration rate, this will also alter the glomerular filtration rate. And so the amount of fluid that gets filtered into the Bowman's capsules, and so this will alter the average glomerular filtration rate. If the glomerular filtration rate is increased or decreased, this can tell us how the kidney is functioning. If it's low, it means that the kidney, there's some problem with the kidney. If it's high, there's also some problem with the kidney. So it's a good indication of kidney function. So we can alter NFR to alter GFR. And so NFR, if you remember, the net filtration rate is equal to the glomerular hydrostatic pressure minus the Bowman's capsule pressure minus the glomerular colloid osmotic pressure. So we can alter net filtration rate by specifically altering the glomerular hydrostatic pressure, which is the blood pressure entering the glomerulus inside the Bowman's capsule. So if we alter the glomerular hydrostatic pressure, we will alter the net filtration rate, which will in turn alter the glomerular filtration rate, and therefore the amount of fluid which gets filtered from the capillary into the Bowman's capsule. I hope this all makes sense. It's important to know. So essentially, if here is the nephron, the head of the nephron, the afferent arteriole on the Bowman's capsule, here is the glomerular hydrostatic pressure, PGH. So if we alter this, we can alter the NFR and so the GFR. Now, the glomerular hydrostatic pressure can be altered by changing the resistant in the afferent or the efferent arteriole. What do I mean by this? So let's just go back to another simple diagram of the nephron and the blood capillary coming in. If there is no resistant on the afferent arteriole, so it's just normal, this would mean that the glomerular hydrostatic pressure is also normal, which is about 60 millimeters mercury. And therefore, if the glomerular hydrostatic pressure is normal, this would mean that the GFR would be normal. However, if there is an increased resistant on the afferent arteriole coming into the Bowman's capsule, this would mean that there would be a decrease in glomerular hydrostatic pressure, and therefore a decrease in the glomerular filtration rate. Now, what if the afferent arteriole is just normal, but there is an increased resistance on the efferent arteriole, the arteriole coming out of the Bowman's capsule? If there is resistance in the efferent arteriole, this would mean that we would have an increase in hydrostatic pressure within the glomerulus, and therefore we would have an increased filtration rate, glomerular filtration rate. So now, let me ask, what would happen if instead of having a increased resistance on the afferent arteriole, we have a decreased resistance in the afferent arteriole? So the afferent arteriole coming into the Bowman's capsule is dilated. What would this mean? Well, this would mean that more blood would be able to rush inside, and therefore this would increase the glomerular hydrostatic pressure, and therefore the glomerular filtration rate. And from all these diagrams, we can see that whatever happens to the glomerular hydrostatic pressure will be the same for the glomerular filtration rate. So if the hydrostatic pressure increases, the GFR also increases. If the hydrostatic pressure decreases, the GFR also decreases. So that concludes this video on glomerular filtration. And this video only looked at filtration, everything to do with filtration, the first step in urine production. In the next video, we'll look at reabsorption, how the filtrate gets reabsorbed back into the blood. And that's the second step of urine production. Thank you.